Imagine a place in the cosmos where gravity is so strong that nothing, not even light, can escape. These are black holes. They are the ultimate cosmic prisons, formed from the collapsed remnants of massive stars. For a long time, we pictured them as simple, elegant objects. You could fall into one, and from your perspective, the journey across its boundary, the event horizon, would be uneventful. You wouldn't hit a wall or feel anything special. You would just drift past the point of no return, unaware of your fate. This smooth, calm picture of a black hole's edge was predicted by Albert Einstein's theory of general relativity, our best description of gravity. It told us space and time behave predictably even at this extreme frontier. But then, the great physicist Stephen Hawking introduced a cosmic puzzle. He discovered that black holes aren't entirely black. They slowly leak energy, a faint glow called Hawking radiation. This process causes the black hole to shrink over billions upon billions of years until it eventually evaporates and disappears completely. This idea created a profound problem for physics. According to the laws of quantum mechanics, one of the most fundamental rules of the universe is that information can never be truly destroyed. Every little bit of information about what fell into the black hole, whether it was a star, a planet, or your favorite book, must be preserved somehow. It can't just vanish from existence. So where does the information go? Hawking's original calculations suggested that the radiation leaking out is random, like static on a radio. It carries no useful information about what the black hole consumed. This created a direct conflict, a cosmic paradox. On one hand, Einstein's theory gave us a smooth event horizon. On the other, quantum mechanics insisted that information must be saved. If the black hole evaporates and the information isn't in the radiation, then it's gone forever, breaking a core principle of reality. For decades, physicists have wrestled with this dilemma, known as the black hole information paradox. It represents a deep crack in our understanding of the universe. This isn't just an abstract thought experiment, it's a battle for the soul of physics. The universe must follow a consistent set of rules. We can't have one law for gravity and a contradictory one for the quantum world. The information paradox tells us that our two greatest theories, general relativity and quantum mechanics, are incomplete. Something has to give. Finding the answer would mean unlocking a deeper truth about the nature of space-time, information, and reality itself. The mystery of what happens at the edge of a black hole became one of the most important and tantalizing questions in all of science, pushing us to explore the very limits of what we know. In 2012, a group of physicists proposed a radical and frankly terrifying solution to the information paradox. They suggested that the event horizon isn't a calm, peaceful boundary after all. Instead, it's a blazing wall of high-energy particles, a firewall. According to this idea, anything attempting to cross into the black hole would be instantly incinerated. There would be no gentle passage into the unknown. Instead, you and all the information you carry would be burned to a crisp right at the edge. This violent end would solve the information problem in a brutal way. The information doesn't get lost inside the black hole because nothing ever makes it inside. It's destroyed at the gate. This firewall hypothesis arose from a deep dive into the strange quantum property known as entanglement. Imagine two particles linked together, no matter how far apart they are. What happens to one instantly affects the other. Physicists realized that a particle of Hawking radiation escaping the black hole must be entangled with its partner particle that fell inside. But for information to escape, that same radiation particle must also be entangled with all the other radiation that came out before it. Quantum mechanics forbids this. A particle can't be fully entangled with two different things at once. To break this forbidden marriage, a violent event must occur, and that event is the firewall. However, this idea was hugely controversial and for a long time, widely dismissed. It directly contradicted Einstein's principle of equivalence, a cornerstone of general relativity. This principle states that a freely falling observer should feel no gravity and perceive space-time as smooth and flat. If a firewall existed, an astronaut falling into a black hole would not have a smooth ride. They would hit a deadly wall of energy. This would mean that Einstein's theory, which has passed every experimental test we've ever thrown at it, is wrong in one of its most basic predictions. The firewall seemed too drastic a solution for most scientists to accept. For nearly a decade, the scientific community leaned away from the firewall theory. Many physicists found it too ugly, too violent, and too disruptive to our established understanding of space-time. They searched for more elegant solutions. Ideas like entanglement islands gained popularity. These theories suggested that information could subtly leak out of the black hole through complex quantum connections, preserving both Einstein's smooth horizon and the laws of quantum information. By early 2025, the consensus was that the information paradox could be resolved without needing to burn down our picture of a black hole's gentle gateway. The firewall seemed like a fringe idea whose time had passed. Just when the debate seemed to be settling, everything changed. In mid-2025, a groundbreaking paper published on the Research Archive, RxIV, presented powerful new mathematical evidence that turned the conversation on its head. Using advanced tools from quantum information theory, the researchers demonstrated that a firewall isn't just a wild possibility, it's an unavoidable consequence of the universe's rules. Their rigorous calculations showed that trying to preserve quantum information as a black hole evaporates naturally leads to the formation of a high-energy barrier at the event horizon. The smooth, gentle crossing described by Einstein was, their math suggested, an impossibility if quantum mechanics is to be believed. This new evidence didn't come from a telescope or a physical experiment, but from pure theory. The physicists built a more complete model of how quantum entanglement behaves around an evaporating black hole. Their work showed that as the black hole ages and radiates away its mass, the connections between the escaping Hawking radiation become so complex that they force space-time at the event horizon to break down. The smooth fabric of reality, as described by Einstein, tears apart and erupts into a chaotic wall of energy. The conclusion was stark. You can have a smooth event horizon, or you can have information conservation, but you can't have both. This was a dramatic shift from the thinking that dominated in the years just before. Until this point, alternative ideas had seemed much more promising. One such idea involved tiny quantum fluctuations, suggesting that black holes aren't perfectly spherical. These imperfections could subtly imprint information onto the outgoing Hawking radiation, allowing it to escape without a fiery wall. Another popular model was the concept of entanglement islands, where a small region of space-time just outside the black hole acts as a portal, allowing information from the interior to tunnel out through quantum entanglement. These theories were clever and preserved Einstein's smooth horizon, which made them very appealing. The 2025 paper directly challenged these gentler solutions. It argued that while those mechanisms might play a role, they don't solve the core problem. The fundamental conflict in entanglement, which first led to the firewall idea in 2012, couldn't be sidestepped. The new proof suggests that the firewall isn't an optional feature, but a mandatory one. This has forced the physics community to reconsider the very nature of black holes. The cosmic debate, which had been simmering down, was suddenly reignited, hotter than ever before. The once unpopular firewall was now back as the leading contender. The confirmation of the firewall hypothesis, if it holds up, fundamentally changes our picture of black holes. It means that the event horizon is not a mysterious gateway to another region of space-time, but a final destructive boundary. Information and matter don't fall into a singularity at the center. They are annihilated at the edge. This implies that the interior of a black hole as we imagined it, a place where space-time is warped to an infinite density, might not even exist. The black hole might be more like a giant, ultra-dense information processor that stores matter on its surface before radiating it away as scrambled high-energy particles. This new reality forces us to confront some of the deepest questions in physics. If Einstein's principle of equivalence fails at the event horizon, what does that mean for the nature of space-time itself? Space-time might not be the smooth, continuous fabric we thought it was. Instead, it might be built from more fundamental, discrete units, perhaps related to quantum information. The firewall could be the place where the smooth illusion of space-time breaks down and its true granular nature is revealed. We are being forced to abandon one of our most cherished ideas about gravity and the cosmos. The discovery of the firewall doesn't end the mystery. It opens a whole new chapter of inquiry. A new set of questions now confront scientists. How exactly does this wall of fire form? What are the precise mechanics that transform the vacuum of space into a furnace? And what does this tell us about the quest for a theory of quantum gravity, a single framework that can unite Einstein's relativity with quantum mechanics? The firewall might be our first real clue, a signpost pointing toward a deeper theory of everything. It's a messy, violent, and complicated clue, but it's a clue nonetheless. We stand at a pivotal moment in our cosmic journey. The universe has thrown us a curveball, revealing that its most extreme objects are even stranger than we dared to imagine. The black hole, once a symbol of the ultimate unknown, is now a laboratory for testing the very foundations of reality. While we may have found an answer to the information paradox, we have uncovered a new layer of mystery. The cosmos is not just stranger than we imagine, it is stranger than we can imagine. And the quest to understand it continues now with a new fire to guide us.